In this lesson, we're going to talk about displaying discrete data. So first we're going to talk about a frequency table. So I've got a list of data here. It turns out there's 30 data points here, and they're all single-digit values. So we're going to create a table that has the different values that were possible, values 1, 2, 3, 4, or 5. That's all that I have here. And then a tally where I keep track of how many of these show up, and then finally the frequency. Frequency is how many times each of them shows up. So what we do is we go through the list and we cross them off one at a time, and we keep track of how many of each we've gotten. So for example, here's a 1, so I tally 1. Here's a 3, so I tally 3. Here's another 1, so I tally 1. 2, 4, 2, 4, 1, 5, 3, 1, 3, 2, 2, 4, 1, etc. I'm just going to finish it off for you. And now I've tallied all of them. Of course, you know this trick about crossing when you get 5. So now I can write the frequencies of each of these values. So 1 occurred 8 times, 2 occurred 9 times, 3 occurred 6 times, 4 occurred 5 times, and 5 occurred twice. So the next thing I want to talk about is if I wanted to have a relative frequency instead of just a frequency. And a relative frequency is basically the fraction of the whole, or sometimes it's written as a percent. So for example, there were 8 ones out of 30, so 8/30ths is technically the relative frequency, but when I multiply that by 100%, I get approximately 26.7%. Or I could write that as 0.267 if you want to write a decimal. Notice that I kept 3 significant figures in this scenario. And now I've completed all the calculations, 9 over 30 times 100%, 6 over 30 times 100%, etc. Now these should add up to 100%, but they won't because of the way we rounded. So here we rounded the 0.6 repeating to a 0.7 for the 3 sig figs. So when you add these up, they'll add up to slightly more than 100% just because of the way this particular set rounded. But if you were able to use them as fractions instead of percents, then you could get them to add up to the correct number, which would have been 1. So if I had written the relative frequencies as fractions instead of as percents and simplified each of those fractions, when I add all of these up, I'll get 30 over 30, or 1. So that's what relative frequency is. Generally, we're going to give it to as a percent or as just a strict decimal, so 0.267, 0.3, 0.2, 0.167, and 0.667, 0.0667, sorry. But you can do it as a percent or as a fraction as well. So now that we know how to collect the data and create a frequency table or a relative frequency table, let's talk about creating a column graph or a bar graph, again, for discrete data. So here's a different set of data. 1, 2, 3, 4, and 5 were the possible values that we could have gotten, and then 5, 8, 7, 0, and 2 happened to be the frequencies of each of these 5 values. So what we do, we create a column graph or bar graph. We have on the horizontal axis is our values, so whatever it might have been. Here I'm calling them values, but they could have been the number of siblings people have, or it could have been the number of pairs of shoes people own, or whatever it might have been. I just counted out something. And then the frequency is going to be on the vertical axis, and you have a normal scale, 1, 2, 3, 4, 5, etc. It is okay to do a little squiggly on the horizontal on the value. So if these started at 11, 12, 13, 14, 15, I wouldn't need the space from 0 to 10. I could just do a little squiggly and then 11, 12, 13, 14, 15, etc. But it is not okay to do a squiggly on the vertical. You always want to make sure you start at 0 on the vertical axis, on the frequency axis. Otherwise, your visuals don't look quite right. So for a column graph, what we do is we go to each value, and above that, we draw a rectangle that surrounds that value and has the frequency that's given. So for example, around the value 1, we draw a rectangle with a height of 5. And so there's our value 1 has a frequency of 5. And now I've finished drawing all the rectangles or bars or columns for each of the various values. Now I want to point a couple things out. The first is that these rectangles do not touch each other. They're separated by space. And that's to illustrate that this is discrete data and that I'm taking one value at a time. So that rectangle represents all of the values, all the times that we had a value of exactly 1. And that's all the values we had, all the times we had a value of exactly 2, etc. And there was a gap between them. There was no 1.5, there was no 1.9, etc. The other thing I want to point out is because there were frequency 0 on the value 4, I still had the value 4 as one of the possible values, but there's no rectangle above it. And we don't want to skip over the 4 and go 1, 2, 3, 5. It's helpful to see that there's a gap at 4. It tells that the values of 5 are further out than we would have expected. We would have expected some 4s possibly, but there weren't any, and that's a meaningful point to our data. So we can squiggle at the very beginning if need be, but we don't want to squiggle in the middle of the values on the horizontal axis. Now, just to illustrate that this is also something you could do, I have created a relative frequency table by figuring out that the total was 22 and then dividing each of these values by 22. And then I've created a relative frequency bar graph as well, where my relative frequency now were 0.1, 0.2, 0.3, 0.4, etc. And I had to sort of eyeball these values because I couldn't get them exactly. So again, that is another thing you could do as a relative frequency bar graph or column graph. So now I want to talk a little bit about describing the distribution. So when your distribution sort of has this shape or maybe this shape, where if you cut it right down the middle, the left side and the right side seem to look kind of the same, or they are symmetrical, then it's called a symmetrical distribution. This one, there's the axis of symmetry here is down at the sort of the low end here, the trough. And then there's 2 peaks, one on either side. We would call this bimodal because there's a mode here and then another mode there. The tops are the modes, whereas this is unimodal where there's only one sort of maximum spot. But, you know, they're still symmetrical, as in the left-hand side and the right-hand side look the same. Now, if they're not symmetrical, then often what will happen is there will be an area where there's a lot of data, and then there's a tail where there's very little data, but there's still some. So if the tail is on the left-hand side in the lower end of the values toward the negative direction, it doesn't mean that they're negative values, but toward the negative direction, we call this negatively skewed because the tail is on the negative side or the lower side. We can also say skewed to the left because that's clearly the tail is on the left. And then positively skewed would be where there's a lot of stuff on the left and the tail is on the right. So it's positively skewed in the positive direction, or skewed to the right. Now you'll notice in this one I drew the bars or the rectangles, and this one I also drew the bars or the rectangles. I could have had bars or rectangles here and here as well. In fact, I didn't actually have to have the sort of blue part on the top. Just the bars themselves would give me enough information to be able to talk about the general shape of the distribution, whether it's symmetrical, negatively skewed, positively skewed, or, you know, unimodal, bimodal, etc. There's various things we could talk about. While I'm at it, I'm going to talk also about an outlier. So if the distribution looks something like this, where there's a bunch of stuff over here, then there's a gap, and there's a value way out on its own, then we would maybe consider that an outlier. Now, visually, you can't necessarily guarantee that what you've found is deserve the name outlier. You can maybe call it a potential outlier, but there's a formula, and there's more than one, but we're going to talk about one particular formula of how to identify outliers later in the unit. So now let's talk about grouped discrete data. This particular example is about the number of cars driving by a school between 8:45 and 9 o'clock on 30 consecutive school days. Now, instead of giving you the raw data, which I could have done with the exact number of cars each of those 30 days, I've grouped that information into groups into what are called class intervals, which are just a range of values. In this case, 0 less than or equal to x less than 10, 10 less than or equal to x less than 20, etc. Notice that the equal to is always on the left bound and not equal to is on the right bound. That is critical. It's always going to look that way. It's less than or equal to on the left side and just less than on the right side. So here, if I got exactly 10 cars on one of those observations, it would fit in this region because of the equal to, and it would not fit in this region because there's not an equal to over there. So it has to be obvious which set it fits into. Now, because this is discrete data, the textbook actually says 0 to 9, because if it's less than 10, the next number less than 10 when we're counting out cars has to be 9. So they're calling it 0 to 9, 10 to 19, 20 to 29, etc. But I don't like that. I prefer to have it written this way. People will know, because it's the number of cars driving by a school, that it's a discrete data set anyway. So the fact that we're using this notation is okay. It's not going to confuse anybody. And then, of course, in the right column of this this table, I've got the frequencies of the different class intervals of the number of cars. Now, when we draw a graph of this, a frequency graph, so I'm going to draw what's called a histogram. And the histogram is very much like a bar chart or bar graph, but it uses class intervals instead of individual values. So there is one small difference, though. On my horizontal axis, I just list 0, 10, 20, 30, 40, 50, and so on. And of course, on my frequency, I have 0, 1 through 10, or whatever it might be. I didn't have to go up above 10 because that was the biggest number there. But I don't have these numbers listed. I don't say 0 less than or equal to s less than 10, or 0 to 9, 10 to 19. I don't label it this way. This is not the labeling of the graph. The graph is like a regular old x-axis, 10, 20, 30, 40, etc. And now what we do is we draw rectangles that span the entire region 0 to 10 with a height of 1. So the first rectangle is going to look like this. And it's covering all of that 0 to 10 region with a height of 1. And then the next rectangle is going to cover the region between 10 and 20, but it'll have a height of 5. And then the next region will cover the region between 20 and 30 and have a height of 10. And so on. So ultimately, our histogram is going to look something like this. Now, there's one difference between the histogram and the bar chart, which is that these rectangles now are touching each other. And that's because we're trying to cover the entire region from 0 to 10, and then the entire region from 10 to 20, the entire region from 20 to 30, etc., rather than just one single value with gaps. Now, the textbook didn't actually do it this way. They draw it like this because they listed them as 0 to 9, so their width is from 0 to 9, and then there's a small little gap, and then 10 to 19, and there's another small little gap, and then there's 20 to 29, etc., and then they have the frequencies up above like that. But I don't think that's necessary because everybody knows when they see this histogram that the 10 here on the 0 to 10 is not included. It's a 0 less than or equal to x less than 10. That's the standard. You do not have to worry about the 10 covering it being part of this region. We know it stops before it reaches 10. So it's okay to draw it this way. That would be my argument. So I'm not going to go with the textbook version. I'm going to go with this version. Now, I do want to mention a couple other things. First of all, that these widths have to be the same. So actually, it's the class intervals directly, 0 to 10, 10 to 20, 20, 30, etc. These have to be the same width. You don't want to have varying width class intervals. It's possible to do, but I'm not going to show you how. Take it as a rule, even though it isn't one. Let's pretend it's a rule that the class intervals have to be the same width, that you don't want to vary the width of the class intervals. Now let's quickly talk about describing this distribution. It looks kind of symmetrical to me, and the modal class is the class interval with the largest frequency is the region between 20 and 30. So the modal class is 20 less than or equal to x less than 30 because that is the class interval with the highest frequency. And that is the end of the lesson.